Hello, and welcome to the presentation of my paper titled A Hybrid Learning Approach to Stochastic Routing. My name is Simon, and I made this paper in collaboration with Ben Yang and Christian Jensen. We are all working at Aalborg University. So I'm going to jump straight right into motivation. So first off, we're in the paradigm of road network routing, and traditionally routing is about finding a path between a source and destination that is optimal in the sense that it minimizes some traversal cost. So we're looking at graphs here, and graphs consist of vertices and edges, and in addition we also have a cost function which accepts an edge as an input and returns a cost of traversing this edge. And in this work we are looking at uncertainty, which means that we have distributions associated with costs. Now, in order to be able to compute the cost of a path, people often use some operators such as convolution, which makes the assumption that costs are independent. And let me show you what that means and why that might be a problem. So say that we have 100 trajectories covering the path ABBC. So as you can see down here, ABBC, and 50 of these trajectories have a have a cost of 30 in total, whereas 50 of them have a cost of 40 in total. Now what we want to do is we want to instantiate our cost function C such that it can accept any edge and return a cost. So we use these trajectories to do that, and we end up with a distribution for AB, which is either that has cost 20 or cost 25, and both of them are probability half. And similarly, if we look at BC, and well, we just copy what we have from the data, right? So either we have cost 10 or 15, which we also saw in the ground truth data, and both of them have probability half because we observed 10 half of the time and 15 half of the time. Now, later on, we might be interested in actually computing the cost of AB, BC again. And the way you can do this is to use convolution. Now, convolution assumes independence between the input distributions. So the way that is done is you look at the two distributions and you go through each possible combination of the costs, and you multiply the probabilities together. So what you actually end up having is this distribution here, which doesn't look like what we had in the input, right? Because we only had 30 and 40 in input, as you can see at the bottom here. But now we also have something, we have a new cost, which is 35, which is of course not reflected at all in the ground truth. And even worse is that this new cost has a very large probability relative to the other ones of occurring. As you can see, 30 and 40 only has probability 0.25, which is a lot lower than we initially observed. So the reason this happens is because we're using convolution, which assumes independence of the two input distributions, but in this case they weren't independent; they were dependent of each other, because we never observed this cross combination. We only observe if the cost is 20 for AB, then it's always 10 for BC, and if the cost is 25 for AB, then it's always 15, right? And this is where we introduce a lot of inaccuracy in the cost of paths for road networks. So the way we consider this is that convolution is an operation, much like plus and minus. It's just an operator, and if you consider it this way, then you can also say, okay, so why don't we just make another operator that instead of computing the independent sum of two distributions, then computes the dependent sum of two distributions. So that's the main idea of the paper, and we use machine learning to obtain this new operator, which we call estimation. So the way we do this is that we input a number of different properties and information into this estimation model, which is a neural network, and it outputs a distribution which is the dependent sum of the two input distributions. So just to illustrate, we have the two distributions here. Then we have a number of extra auxiliary properties that we also input. And the idea with these is that they, to some extent, may have an impact on the dependence of the two distributions. So for instance, just to give an example, if we have a traffic light between the two edges, then you might have the case where a car decelerates before the traffic light and then accelerates afterwards, which means that there's some dependence here, because the other option is that it just continues at the same speed before and afterwards, right? There's no option where it continues at the same speed before and then accelerates afterwards, or at least initially or intuitively there shouldn't be. Right. So we implement this, and it turns out that our estimation model is not always, well, it's not perfect, and that can be expected. But the problem is that sometimes the two edges are just not dependent on each other in terms of costs, and this can, for instance, be because the input data is not full trajectories, but rather segments of trajectories. So if you already split it up and you have this, if you have data for A, B, B, C, and you have for another edge and BK, for instance, then if you want to combine A, B, BK, but you don't have data that covers both of them, then it's sort of independent already. So you can't really apply the dependent operator to this. So what happens is that convolution turns out to be better in that case, right? And in some cases, convolution is just better because there's not a strong dependence between the two costs. So we end up with the figure that you see here, where we measured the KL divergence for a significant number of convolutions and estimation operations, and then so this is compared to the ground truth, of course. And we had the idea to try and combine them. So why not have a classifier, which is what we implemented, that determines whether to use convolution or the neural network, and then applies the one that is chosen. And this is the hybrid model in a nutshell. So as you can see, both the spread and the median KL divergence here is a lot lower than both the neural network and the convolution can produce. Now, so far we only considered two adjacent edges, and of course we also want to be able to compute the cost for any path of arbitrary size. So the idea is that we have a path, and we want to compute the cost for the full path, and what we take is the cost for the pre-path up to the last edge plus the cost of the last edge, and we combine those and we obtain the cost for the full edge, right, or full path. So looking at the path we have here, A, B, B, C, C, D, you might say, well, the cost of this full path is to be obtained by combining the cost of A, B, B, C, so this part here, with the cost of CD. Now, the cost of A, B, B, C is obtained by having the cost of AB plus the cost of BC, right? So it's sort of an incremental approach. Sorry. So it's an incremental approach where you sort of continually add edges on top of the path as you expand outward, and you don't have to recompute the cost for the full path every time, but rather just add onto it essentially. And this property is very essential for routing, because during routing you have path expansion, you don't have path recomputations, and it's very expensive to have to recompute the cost for the full path, whereas if you can add on top of it, it's a lot cheaper. So we wanted to do an experiment to see, well, okay, so our model is trained on edge pairs, but what happens if we just follow this idea that we just have and just continually add edges on top, and we use our models to compute the cost of longer paths than that? Well, this is what happens. As you can see, the probability ratio, so it represents the likelihood of either convolution or estimation being better. And as you can see, estimation becomes progressively worse as you add more edges in the path. And of course, this is mainly because the models were trained on 2 edges, and there's a big inequality in the cost between the 2 edges as you start adding more edges. But yeah, anyway, what we learned from this is that you should not apply estimation more than a number of times before applying convolution. And this doesn't restrict you from ever using estimation again, but rather just you have to use, at some point you have to use convolution, and then you can go back to using estimation a number of times. So we come up with a technique where you build segments, cost of segments, and then add them together at some points, and then don't have to you have to maintain several costs for a path, but you never have to recompute everything, which is of course the big benefit of doing it this way. Finally, I wanted to talk a bit about some experiments we made. So first of all, quality. I think there's a few things I need to explain here. So we have 4 paths we're looking at here. Now the number, so infinity, 1, 5, and 10, these numbers represent the amount of time that we are giving to the algorithm before it has to terminate and return a path. So it's sort of a time limit, you could say. And we have an anytime algorithm that returns at the point given by the user. So you can say, well, it has to return after 20 seconds. That's that's the latest point. It can return before that, of course, but at best it spends 20 seconds and not more than that, or at worst. Right, and then we have distance categories. So these categories represent the distance between the source and the destination, and that's the Euclidean distance between the two. And we have 100 paths for each category, and then we simply make a query, and we see, well, so the percentages here represent how often we obtain a path that is different than what Dijkstra produces. And the reason we do this is because if we always obtain a path that is the same as what Dijkstra obtains, then there's no reason to look at dependent cost, because Dijkstra assumes cost independence everywhere, right? It's sort of the standard way of doing it. You assume cost independence, and then you just expand outward and have fun, So in this case, for short paths, we also find that we mostly find the same path as Dijkstra, because there's, typically not so many options for which direction you can go and how you get to the destination. However, when you start looking at longer paths, so 1 to 5 kilometers and onwards, you actually very often find a path that is different from Dijkstra, which means that there is some promise in actually looking at dependent costs and routing using that. Finally, efficiency. So I just wanted to show the mean execution time of different distance categories. As you can see, 5 to 10 kilometers is actually quite expensive in terms of runtime, and the reason for this is because there's few outliers that really drag up the mean quite a lot. And of course, the main reason for having expensive runtime is that there's a lot of overhead in terms of using estimation models and machine learning models. So you have to prepare the input features, and you have to run the simulation, and then of course you also have to somehow extract and work with the output. So yeah, that's the main reason for what you might find slow run times. And finally, just to conclude, so we proposed this hybrid model that uses both machine learning and a convolution. And to go with that, we also propose a routing algorithm that complements this hybrid model. And we show that using this approach can produce paths different to Dijkstra's algorithm because of the consideration of spatial dependence. And finally, we also introduced this incremental property in terms of, in combination with machine learning to support incremental path building and cost computation, and having completely to avoid recomputation of costs. And thank you for listening, and have a nice day.